Chapter 5, Section 4, Part 2. We're solving radical equations, and while we are solving these, something interesting happens. It doesn't happen all the time, but it is a reason why you should always check your answers. We get extraneous solutions, or extra solutions that are not actual solutions. We get an answer, but it doesn't work if you plug it back in. So you need to check when you're solving with radicals, especially when these kinds of situations happen, where there's a free x and an x inside of a radical. What we're going to do to solve it is we're going to get the radical gone, get it by itself, and then get it gone. So right now it's by itself. Now we just have to get it gone. That leaves us with x squared equals x plus 6. Making marks over here. Then we're going to move everybody over. I like to keep my x squared positive. X squared minus x, that's supposed to be a 6, minus 6 equals 0. Then we're going to factor. Factors of 6, that subtract to negative 1. Well, that would be 2 minus 3. So x is negative 2 and positive 3. But we should check them. So let's see. 2 equals the square root of 2 plus 6. Sorry, negative 2. Negative 2 equals the square root of 4. Negative 2 equals plus or minus 2. So yeah, kind of works out. Okay. And we need to try 3. I mean, really, if you got the positive one, it doesn't. So it's like, sort of. 3 equals the square root of 3 plus 6. 3 equals the square root of 9. 3 equals 3. Yeah, that one works a little better if you assume that it's positive when it comes out of there. That's a for sure check. The other one doesn't. Remember, we can do y, where'd it go? Equals x, the left side, and y equals the square root of x plus 6, the right side, and we can look at where that goes. Oh, that's a y equals y. I meant x. Y equals x plus 6, and where they graph together, just this one. So what they're saying is if it comes out positive like this, and you start it out negative, that's a no-no. But if you come out positive, and you start it out positive, that's a yes. So be careful on your extraneous solutions, okay? Ouch. So, solve and then identify any extraneous solutions. Well, move that 13. So the square root of 5n equals negative 10. I'm going to square both sides. 5n equals 100. Divide by 5. N equals 20. So we should double check it. 13 plus 5 times 20 equals 3. 13 plus the square root of 100 equals 3. 13 plus 10 equals 3. 23 equals 3. No. So no real, that says red, real solution. And we could try and check it as well. Let's see. Y equals 13 plus square root of 5x, and y equals 3. They don't touch. So there's no real solution. Okay? Good, check. Solve the equation, check your solutions. Well, before I start doing them, pause it, give it a try, see what you come up with, see if you find any that don't work. Let's look at 11. All right, square both sides. 4 minus 3x equals x squared. I'm going to add 3x and subtract 4. So 0 equals x squared plus 3x minus 4. Factors of 4 that subtract to 3, those do exist. x. That would be 4 minus 1. So x equals negative 4 and positive 1. And we should double check them. Let's see. Negative 4 times negative 3 is positive 12. 12 plus 4 is 16. Square root of 16 is 4. I'm going to say that one's a no. 1 in there. Square root of 1 is 1. That one does work. So I would say x equals 1 only. And we could graph it just to double check. Square root of 4, y equals the square root of 4 minus 3x. And y equals x. One spot. 1, 1. Okay? Good to go. Let's try the next one. Subtract 10. The square root of 3m equals, that's a 10. I was thinking ahead. Negative 9. The square root isn't going to be a negative. This is where you could be like, it's already going to not be a real answer. Because once I square, once I square both sides, and then I get 3m equals 81, then we divide by 3, and we get m equals 27. And then we try to put it in there, right? 3 times 27 plus 10 equals 1. The square root of 81 plus 10 equals 1. 9 plus 10 equals 1. 19 equals 1. No, it doesn't. So, no real solution. Doesn't happen. You could graph them. It ain't going to touch. 13, since that's a little muddy, I'm going to change colors here. We're going to have to square this guy and square that guy. So we got 7p. Actually, I'll do that squared first. P plus 1 squared. The pattern of doing a binomial squared is the first thing squared, multiply together times 2, so 2p, and then 1 squared equals 7p plus 15. Subtract 7p. P squared minus 5p plus 1 equals 15. Subtract 15. P squared minus 5p equal minus 14 equals 0. Factors of 14 that subtract to 5, that is possible. We're going to have 2 minus 7. It's going to be negative 5. So p equals negative 2 or positive 7. And we should plug both back in. Negative 2 plus 1 is negative 1. And we're not going to get a negative out of that square, so I'm going to say negative 2 is out. 7 plus 1 is 8. 7 times 7 is 49. 49 plus 15 is 64. The square root of 64 is 8. That one checks out, so I'm going to say p equals 7 is our better answer. Okay? Everything we've been doing, but a real-world situation. The period p in seconds, so it's time, of a pendulum is given by the function p equals 2 times pi times the square root of L divided by 32, where L is the pendulum length in feet. A pendulum has a period of 4 seconds. Is this pendulum twice as long as a pendulum with a period of 2 seconds? Explain your reasoning. So if we have one with 4 seconds, pi square roots of L divided by 32, we need to get L by itself. I'm going to divide by 2 pi. That reduces, so we get 2 divided by pi equals the square root of L divided by 32. And then let's square both sides. And so we get 4 divided by pi squared equals L over 32. And we multiply by 32. We get whatever that is. 32, 120, 128 divided by pi squared equals L. So 128 divided by pi squared, nope, pi squared is about 1.82. We want to know if it is twice as long, okay, with a period of 2 seconds. So if we plugged in a 2 there instead, so let's do the one with a 2 there instead. 2 equals 2 pi square root of L over 32 divided by 2 pi. So you get 1 over pi equals the square root of L over 32. That's an L, I promise. Square both sides. So 1 over pi squared equals L over 32 times 32. So 32 over pi squared equals L is, say, if we doubled, is the pendulum twice as long as the pendulum with a period of that? Well, 2 times 32 would be 64, not 128. It's actually 4 times as big. Let's see. If we do, oh, that's supposed to be 128. There we go. 12, back to greenie. 12.97 is what that was. And go back to bluey. And instead of 128, go back up there. Let's do 32. 3.24. 3.24. Well, let's do 12.97 divided by 3.24 is about 4 times. So, no. It's 4 times as long. There you go. That's what it's like. Here's another. What is the length of a pendulum that has a period of 2.5 seconds? So we're just going to plug it into that same deal. 2.5 seconds equals 2 pi L over 32 divided by 2 pi. 2.5 over 2 pi equals the square root of L over 32. Square both sides. 2.5 over 2 pi squared equals L over 32 times 32. So, squiggly lines is what that's supposed to be. Squiggle, that's L is approximately. Now, why did I wait for all of that? 32 times, no, still not times, times the quantity 2.5 divided by 2 pi squared. So 32 times 2.5 divided by 2 pi squared is about 5.07 when we round it. Should be something like that. Forgot to tell you to pause it, but just went ahead and showed you how to go. Just plugging it in. That's all it was. Waited till the end to do everything so that it would be as little rounding as possible.